Hello, today's topic is about LU factorization. It's also called LU decomposition. By LU factorization of a square matrix A, we mean we can express it as the product of a low triangular matrix and the upper triangular matrix A, or we simply write it as LU. Okay, and why should we do that? That's a question. Okay, so far we know for a system of n equations in n unknown, we can express it in matrix form like this. And we work it on its augmented matrix with Gauss elimination. And our purpose is to arrive at a system, equivalent system like this. That's Gauss elimination. And this is an upper triangular matrix. Upper triangular matrix. Below the main diagonals are all zeros here. Okay. And then we also know how to solve such a system. And the method is what? We just solve such a system by the back substitution method. Okay, from you do multiplication of these two vectors, and it's equal to this bm. So we have ANM, A sub NN times X sub M is B sub M. So therefore we can find XM. From this we can find X sub M. And then we pass that value to the equation right above this last one. We have, and as you can see, if we have more, yes, if we show that row there, you will see it's A sub M minus 1, M minus 1, X sub M minus 1 plus A sub M minus 1 M, XM is equal to that B sub M minus 1. Now XM is known, so we solve this equation for X sub M minus 1. Yes, this gives us X sub M minus 1. And yes, we can continue. Just backward, we find, eventually we find x1. We find x sub 1. Okay, that's this, the Gauss elimination. Okay. Of course, with Gauss elimination, we work on the augmented matrix from top to bottom. How about if we work from the bottom to top? Use all the elementary row operations. Okay, as in Gauss elimination, we can change the system to such a system, such an equivalent system like this. And this is a low triangular matrix. Okay, low triangular matrix. Non-zero entries are in the low triangular. And all entries in the upper triangular, they are all zero here. I mean above the main diagonal, below the main diagonal. Okay, so in this case, how to solve such a system? As you can tell, we will solve it by forward substitution. Okay, you do multiplication, you have A sub 1 x1 is B sub 1. Solving this system, we can easily get x1, right? X sub 1. And therefore, after this gives us x sub 1. Now we pass that value to the second equation. We have a sub 2 1 x sub 1 plus a sub 2 x sub 2 is equal to b sub 2. Now x sub 1, x1 is known. Okay, we solve this for x2 for this. That gives us x sub 2, and we continue this process, and eventually we'll find x sub m. Okay, so if we are lucky enough, the given system is just such a way, we can solve it easily, right? Okay, no Gauss elimination, no matrix operations are needed. Okay, now that's why one reason, okay, why we need LU factorization. Now we have this question. Given that we already have an LU factorization, how to solve such a system? That system will be A is equal to LU, L times U, X is B, right? Solving such a system is equivalent to solving this one as the same. Okay, now imagine we have parentheses here, and let y be ux. Now this will be L, y is b, where L is not known, b is known. So we solve this for y. Solve for y. Okay. That's the first step. 1, we solve for y. Second step, 2. Now, here, ux is y. The first step gives us y value, so y is known, u is known. So we solve this for x. That's our purpose. Our purpose is to solve such a system for x. Yes, solving for y is not our purpose. So therefore, given that we have an LU factorization, and we can just take these 2 steps to solve, yes, the system x is equal to b. Yes, it's solved this way. Okay, so that's nice. Okay, no matrix operations are needed. Given that we have LU factorization, yes, LU factorization also finds other applications. One application is this. Let's say, how about, given that A is invertible, how to find its inverse matrix, A inverse? And we know A times A inverse is I, right? The identity matrix. So now A is, given that we have LU factorization, that's LU A's inverse is I. And we want to find this matrix, the inverse of A. So given that A's inverse has columns E, say B sub 1, that's a column vector, B sub 2, second column vector, and B sub m, n column vectors. Okay, now we know this. Now LU times this is LU times this. Therefore, it's LUB1, LUB2, LUB sub m. Okay. Now we know its identity matrix is E sub 1, E sub 2, E sub m. And you know what's E1. How about E1? Okay. Any clue about E1? E1 is a column vector of the identity matrix. Therefore, here, E1 is this. E1 is 1, 0, 0. That's E1. E2, as you can tell, is 0, 1, 0, 0. Yes. I mean, this is dot. Okay. And as you can tell, you can find out each all the corresponding E sub m, E sub I. So these two are equal to each other. Therefore, the corresponding pair of column vectors must be equal to. So LUB1 sub 1 is E1. LUB sub 2 is E sub 2. Or simply we put it one way in the shortcut. BI, EI. I changes from 1, 2 until n. Yes, therefore, as you can tell now, we just apply the very skill we just know. We just studied how to solve, yes, answer the third question, or the question how to solve a linear system using LU factorization. Now you apply the same skill, you do it. We can do it. We finally review again. Okay. Recall this. And the force stable, what? Solve Ly is E sub I for y. And then solve UBI is y equaling to y for B sub I. Yes. Okay. Now we can find each column of the inverse matrix, and therefore we find the inverse matrix. Okay. That's why we should have this. Okay, OU factorization, and now we'll study how to obtain OU factorization of a square matrix. And as you already know, we do operations on which one? On matrix. But yes, we apply elementary matrix operations on A. We can change it to eventually by Gauss elimination we'll arrive at an upper triangular matrix, right? Okay, and now we assume there is a special assumption here. We assume there is no row interchanges. Yes, we have three elementary row operations interchanging two rows. That's just one. Now we remove this one. So it means in all the Gauss elimination from this A to the corresponding upper triangular matrix, we only apply the other two elementary operations. Okay. You apply one operation to a matrix A you'll get another answer matrix. This is equivalent to multiply this with one matrix. It's called elementary matrix. That matrix reflects the operations, the elementary operations. Say for example, if we have, how about this? E is this. Given that we are working on a 3 by 3 matrix, if it's the fourth row times 5, that means 5, 0, 0, 1, 0, 1, 0, 0, 1. It's the identity matrix. It comes from the identity matrix. That's 1, 0, 0, 0, 1. Okay. The fourth row times 5. Yes, so the very elementary matrix will be like this. Okay. The fourth row multiplied by 5 times 5. Okay, it's this. How about if it's the fourth row times 5 added to the second row? Yes, it's from this identity matrix. If this fourth row you want the matrix A, okay, you want to work on matrix A. The fourth row multiplied by times say 5 and added to the second row will be this. How about to the third row? Yes, as you can tell, that will be this. The very corresponding elementary matrix. If it's the second row of a matrix, you want to multiply the second row and add it to the third row. Yes, same. If the second row times 7 added to the third row, yes, from this second row times 7, you add it to the third row, you get this. Okay, now with this reviewed, okay, so we start with the matrix A and we apply the elementary row operation on it. So it's equivalent to this. You have the elementary matrix, you do the multiplication, you get an answer matrix. And with this answer, if it's not an upper triangular matrix, we still can apply another elementary operation on it. Given that, therefore, it's this, its corresponding elementary matrix, and so on. You do this. Okay. Eventually, of course, we can remove the parentheses. Eventually, if we have k steps, k minus 1, e2, e sub 1, a, that will be an upper triangular matrix, right? It's an upper triangular matrix, given that this is U. Oh, we want LU factorization. We say, hey, this is our U. Now, what's L? What's L? The problem is, what's L? Okay, you say, oh, we should know that each elementary matrix is invertible. You can change from the very one, say any one elementary matrix, you can change it back to the identity matrix. Okay, so you can change it back, so each one is invertible. Therefore, their product is also invertible. Their product is invertible. So therefore, A is this whole thing, E sub k, E sub k minus 1, E sub 2, E sub 1. This, the product's inverse, okay, times U. And now, hopefully, this is L. And L is this. Let L be this. you can say let L be this, and that will be equal to, if you remember, if you have, yes, this is covered in linear algebra, is this E sub 1 inverse E sub 2 inverse AK minus 1 inverse AK inverse. Okay, you say, oh, that will be LU. And we know U is upper triangular. Now, is L low triangular? Is a low triangular matrix? That's a question. It turns out, yes, it is. Why? Why? To answer this question, okay, we go back to our assumption. No row interchange. There is no row interchange in all the process, the Gaussian elimination process. Okay. Now you have, therefore, you will see, how about is L low triangular? Okay. Now we need to know this. E sub 1, each one, the inverse, are they, how about this? Is each one the inverse matrix of the corresponding of the elementary matrices? Are they all low triangular? We have a theorem. When I prove it in linear algebra, we can prove it. It's not difficult to give a proof. Okay. Because no row interchange, we always work on a matrix. You just do it. You work. If you are working on the nth row, we try to use it to do what? To eliminate the terms below it, right? So you are not working on the top one. So therefore, the operation is always this. It's a low triangular. It's, hey, this row times something added to this row, to this row, to this row. So those terms, they could be non-zero. Okay, so it's a low triangular. Each elementary matrix here in this very context, given that there is no elementary no row interchange. Okay, so each one is a low triangular matrix. It's a low triangular matrix. And in linear algebra, we also have a theorem. The inverse matrix, given that the inverse matrix of a low triangular matrix is also a low triangular matrix. And on the other hand, we also have that one. If a matrix is upper triangular matrix, its inverse matrix is upper triangular, given that it's invertible. Okay, so that shows this. Okay, they are each one a low triangular matrix. We have a theorem. The product of a low triangular matrices is also a low triangular matrix. So therefore, this A, that's proved. Okay, this is the L is really low triangular. Okay, and that's LU factorization by Gauss elimination. So it turns out this very talk, I cannot make it too long. And if I show you 1, 2, or 3 examples, work with some simple examples, okay, and then you'll find it's this way. Okay, there is a shortcut, and if you are interested in this, and you can refer to this. You can take a screenshot of this. Okay, it's this. You see, we say, hey, L is which one? Do you remember that? Is 1 inverse, A2 inverse, EK inverse, right? It sounds like, oh, it's a lot of work. We need to find the inverse, and then find their product. That's a lot of work. Okay, sounds like a lot of work. And actually, if you take some concrete examples, you work them by hand, it's really time consuming. Okay, and you'll find the rule. We don't need to do this at all. In the process of Gauss elimination, for finding U at the same time, we can set up L easily. How to set up is just that way, the rule. And okay, and I repeat this, and then okay. So in general, simply speaking, okay, in summary, the algorithm should be quite efficient. Okay, if we really needed to, we had to find the inverse and find their products, and the time performance will be horrible. Okay. So that's the fourth method, Gauss LU factorization by Gauss elimination. And there is another method. It's called cross method. That method, okay, assumes for such a square matrix we have this decomposition or factorization. This is L, this is U. With U, all entries on the main diagonal are assumed to be 1 each. Okay, and so, and you can easily figure out the rules like this. Okay, the rules like this. And say, for example, how about A11? A11 is given by this fourth row times the fourth column, right? The fourth row of L times the fourth column of U. And you know A11 is simply L11 times 1. That's yes, therefore L11 is just A11. And you can find how about the same A21 that's given by the second row of L times the fourth column. So you have A21 is L sub 21 times 1. Yes, you have this. And the same way you can find all those. You can find the fourth column of L so easily. And you can also find the fourth row of U easily. Okay, and you set up you figure out the rules like this. We have rules like this. Finding entries here, those entries. Okay, you have the rules here. And the direct translation to computer code is like this. Okay, I don't give you explanation about the code. It's quite straightforward. If you get used to for do those loop statements, that's just quite straight translation conversion. Okay, so the code is so short. It's just a few lines, 20 lines or less. Okay. Gauss elimination, the method LU factorization by Gauss elimination also is about 20 lines of code. Okay, that's this. And of course, and there you may have some questions. Hey, with Gauss elimination, we assume no row interchanges at all. How about we must do row interchange? How about that? And that's a way when we do Gauss elimination, we have which one? We have a pivoting issue. Yes, you have. Sometimes we have to. And therefore, the approach will be like this. 2 steps. First, given that we know all the row interchanges beforehand. Now, all the row interchanges will be like this: E sub 1, E sub 2, or E sub 1, just some number. Okay. The operation, accumulated operation is like this. The product of all the necessary elementary operations, or the product of it's this. Okay, k minus 1, k e2 e1. Yes, it's this. You work on this one, right? Yes, therefore it's this. This will be a matrix. It's a if it's simply about the row interchanges. Okay, each one will be, say, how about if it's a 3 by 3 matrix, you interchange, it comes from I. Okay, it's this. Okay, if you interchange the fourth row and the third row, it will be this. Third row, second row, fourth row, right? Yes, you get such a thing. And each one will be like this. Each one will be like this. Okay, you interchange 2 rows. And their product, it turns out, also will look like this. And such a matrix is called a permutation matrix. What can you tell about this? What kind of a special feature can you figure out here? We just observe. Okay, we can see each row, every column has only one. All others are zeros. Yes. So it turns out that if we have a system AX equals to B, now each side we multiply by such a permutation matrix Q, such a Q. Yes, therefore to solve this, and it turns out and QA, now we can do LU factorization on QA, because we know after that and no row interchanges are needed. So therefore this system will be LUX is QB, right? Now you know how to solve it. How to solve it? Okay, review. Well, we solve LY is QB for Y first temporarily. 2, we solve my goodness. We solve UX is Y for X. Yes. Okay, so now because that's the second, we have another one. Okay, another result is this, and QA could be factored out as LU times U. Now, such a permutation matrix is always invertible, therefore A is Q's inverse times LU. Okay, now you don't want to write this, we simply replace it with P, well, PLU. Well, P is just Q's inverse, right? Okay, so such an A is expressed as the part of a PLU. That's called PLU factorization. Okay, that's the topic. Yes, for today anyway. And LU factorization is commonly used. Okay, so therefore, MATLAB, Mathly, LUO plus Mathly, and Julia, they all provide a built-in function LU. You pass a matrix to it, it will give you, like if you use LUO plus Mathly, it will return a matrix, low triangular matrix, and up triangular matrix. Okay. So when you do assignments for this course, you take test, you may simply call this way. You don't need to spend time to find how about you spend time to study how to find error, how to find a U. Now you just directly use it. Okay, the very idea you should know just in summary. Okay, how to solve this again. That's our topic, and especially it's the most important thing of this talk. And given that we have LU A is factored out as LU. Okay, it's this. We take two steps. One, solve Ly equals B for Y first, and two, solve UX is Y. We imagine this is Y for X. That's our purpose. Okay, so that's it. And I also wish you know how to use it to find the inverse matrix of A, given that we have LU factorization. That's it. Thank you for watching.